So we were discussing about average cost problem, average cost MDP. So I have my cost function here. I want to minimize over all mu j of mu equals to 1 over t summation t equals 0 to t minus 1 CIT UT IT plus 1 given UT equals to, or maybe UT is simulated according to mu IT. So this is our objective function. What we were concerned with is whether a solution for this exists, and if so, how do we compute mu star? Mu star, the policy, is what we want to compute. Sometimes you will see me writing UT equals to mu IT, and sometimes I will write mu T simulated as a conditional probability, because sometimes policies could be randomized, in which case this is the correct notation. Sometimes policies are deterministic, so this is the correct notation. Because we are, I guess, in some cases randomization would make sense, but I'm going to be using these type of notation interchangeably. So depending on the context, you can think of it as a deterministic map, or you can think of it as a randomized policy, and UT needs to be simulated according to that randomized policy. Yes?
So earlier you argued that there was no point.
No point randomizing.
Is that because we only considered the finite horizon? Is it different in this?
This one is infinite horizon. Sorry. Oh my God. Okay. I need to take limit t goes to infinity.
But is that why?
No, that's not the case. Sometimes when you are doing reinforcement learning, you start with a randomized policy and then you converge to a deterministic policy by the end of the, after the end of the learning process. So that's why I want to make sure that I use both these notations throughout the course, because when we get to the learning algorithms, reinforcement learning algorithms, we almost always start with a randomized policy and then move to deterministic as time progresses. Like we learn what the best deterministic policy is. Yeah. But from the theoretical point of view, there is no point doing randomization in MDPs. Okay. So it's because this is a reinforcement learning class, not an MDP class. So I'll use these two policies interchangeably, these two notations interchangeably. Okay. So let's study some specific. So one of the things we talked about in the previous lecture was transient states. And then recurrent states. So transient states, you visit them a few times in the early stages of your decision process, and eventually you move to the set of recurrent states. And we also talked about unichain condition. And what that means is, for every mu, there exists a single recurrent class. And a few transient. You can have empty set of transient states, so you can have a few transient states, that doesn't matter. But you have to have a single recurrent class for every policy mu. Okay, so let's look at some examples of situations where there is a single recurrent class. So let's think about, how many of you go to Kroger or Whole Foods or Giant Eagle for shopping? I'm assuming everyone. As long as you are cooking, you have to go there, right? So how many people are in the queue before you at the checkout counter? So let's say you only use the self-checkout counter, so you have like 6 or 8 different self-checkout machines. How many people are ahead of you, typically speaking? 2, 3, 0, 5. Okay, so those are the recurrent states. Have you seen 10 people ahead of you in the checkout counter? Not quite. There is a possibility that there could be 10 people, but generally speaking, we don't really see 10 people. So those are transient states, okay? We don't really see that state coming often. Most of the times what we see is recurrent state. So 0 to 5 would be a recurrent state because you see 0 to 5 people in the checkout counter, but 10 or 11 or 12 or 100 would be a transient state in that particular situation. We never see 100 people, and even if there are 100 people, that queue will get flushed fairly quickly. Okay, so that's the situation of transient state. Let's think about another example. So football Saturdays. How many of you have driven to the campus on football Saturdays? Not okay. Someone, okay. A few people have come to campus on football Saturdays. So there are two specific things that happen. So before the game starts, there's huge influx of cars coming into the campus, and after the game ends, there is a huge influx outflow of cars that are going out of the campus. So if you are at the traffic light, you might have 100 or 200 cars in front of you or behind you. Okay. That's a transient state, okay? It's not the steady state. It's not what you see on a regular basis. On a regular basis, you will have 10, 15, 20 cars ahead of you, and that's pretty much it. If you come at night, there will be 0 cars in front of you. So what unichain condition says is you have a single recurrent class, a set of states that are visited infinitely often, and a few transient states. It could be empty set, it could be a few transient states, but those are transient states, which means that it will happen in the beginning, but then eventually it will die down. Those states will not appear again. So most of the times this sort of situation appears in queuing systems, and most of the times in queuing systems we are looking at average cost problems because we worry about the steady state performance, whether it's wireless networks, whether it's traffic and transportation system, or whether it's queuing in a store. Okay, so in all those cases, we care about the steady state performance. We don't really care much about the transient performance. So many a times when you go to places like Whole Foods or Kroger and they see a long queue of customers waiting at the checkout counter, they'll start opening up new checkout counters and try to flush that queue out. Okay, so that's their policy. That's Kroger's policy. If you look at the traffic light signals, okay, so the traffic light signals is a stationary policy. Okay, so they tune the traffic lights at one point of time, wherein they say that, okay, these lights will be red light for 1 minute and then they'll turn green for 30 seconds and then it'll turn red light for 1 minute and green for 30 seconds. And then in the cross intersection, whenever this is red, the other one is going to be green and vice versa, right? And then there is a small, like 2 or 3 seconds of yellow light in the middle. So those are stationary policy, and one of the things that is happening at the traffic lights, like that's the new stuff that is happening at traffic lights. They want to make traffic lights more safer for pedestrians. So now earlier traffic lights were designed for vehicles, but now they also need to design traffic lights for pedestrians. So they need to come up with better policies, for switching and signaling and yellow light and green light and red light and how much time, because they want to make sure that you don't queue up a lot of vehicles, so you serve the vehicles that are coming at the intersection, but at the same time you're also serving the people who are crossing the intersection. Okay, so something that people in civil engineering and transportation engineering worry a lot. Any civil engineers here in this class? No civil engineers? Okay. But anyways, if you go to work for a company which designs traffic lights, and that's something you worry about all the time. And there again, you worry about the average performance. You don't worry about the transient performance. Okay. EV charging station. So if you were, let's say you are director of EV charging stations at Tesla. Okay, so then it's your mandate to figure out how many EV chargers to put at shopping malls, at Whole Foods and highways and so on. And again, at EV charging station, there will be queuing of electric vehicles wanting to be served throughout the charging process. And so So that's there again, you need to come up with some sort of policies about how many EV chargers to put, how do you do EV charger sharing between multiple vehicles. So nowadays there are some EV chargers where you have one station serving 5 or 6 different cars. So if 6 cars are connected, each car will get lower amperage, like lower current. On the other hand, if there is only one car connected, then they'll get a much higher current. So there is some sort of policy that you need to design. And in those cases, you might have multiple types of customers also. So some customers could be premium customers, so they need to be served upfront. Some customers would not be premium customers, like all of us. So we won't get as much priority during the charging process. Okay, so this particular thing has a lot of different applications. So even though much of the class is about discounted setting, I still want to talk about average cost MDP, because whatever we study in the reinforcement learning part of the class would be applicable to the average cost setting as well. And a lot of different places where you would go to after you complete your graduation, you would be potentially solving this problem. But the theory, so the thing with average cost MDP is that there aren't a lot of papers written on average cost. Almost everybody studies discounted cost because the number of assumptions we require in discounted setting was very small, right? We only required bounded cost and we required alpha to be less than 1. That's it, right? But in this case, we need to make assumptions about transient states, recurrent state, single recurrent class and all that stuff, and it's too difficult for. And then while I'm doing the talking about the results about the average cost, you will realize that there is a lot of machinery that goes on behind average cost MDPs. Any questions on this, average cost MDPs? Do all of you understand the examples, the business settings where the average cost MDP is useful? Yeah.
Just a quick question.
Yes.
We assume there is a single recurrent class.
Correct.
Do we know exactly which states are recurrent, or we just assume there exists, but we don't know which states are transit, which states?
Given the application, sometimes you know what the recurrent states look like.
We already know.
Yeah, you will already know what the recurrent states would be.
Okay.
But for different policies, you can have different recurrent classes.
Oh.
Okay? So for some policy, you will have one recurrent class. For other policies, you might have different recurrent class. Okay? So you don't have a unique recurrent class for all the policies.
Oh.
Okay?
Oh, yeah. Makes sense.
Any other question? Okay. So what is the main result here? So you have a unichain MDP. For every mu, there exists a G mu and a V mu. So G mu is a scalar. So let me. G mu is a scalar. V mu is a value function such that C I'll have to maybe write the whole thing. So summation of J P J given I mu I C I mu I J plus V mu J equals to what should I write? This should be V mu I plus G mu. Actually, I probably want to give it a notation. So T mu of V I equals to summation over J P J given I mu I I'm going to use this notation. Yeah, okay. So remember that there is no discount factor alpha here. So this is the same Bellman operator. It looks like a Bellman operator, but with a mu, with a specific policy mu. And there's no discount factor here, so alpha is missing. There's no alpha. Alpha is equal to 1. Again, you can think of it as deterministic or stochastic. So in the case of stochastic, then you have to do the averaging with respect to the actions here. Any other question? Okay, so what is G mu? It's the total or average cost starting from any state I in S. So G mu doesn't depend on it doesn't depend on the state from which you start in this case, and V mu has a very specific property. So V mu would be the limit t goes to infinity 1 over t summation t equals 0 to t minus 1 c minus t minus 1 or t G mu. So this depends on I. This depends on I0. And I want to condition it on I0, the initial state. So in some sense, this is the error, or not error, but what should I say? The transient performance minus the steady state performance. Some sort of error, transient minus steady state. Let me write it that way. So whatever is the transient cost accrued starting from state I naught minus whatever the steady state cost you would have accrued starting from I naught. So that's what roughly what this V mu quantity, this is what it is capturing.
Why there is a t in the second item? Because
This t?
Yeah.
Okay, I'll explain that in a bit. So remember that this is a bounded cost, okay? So I'm adding up, oh, there is a, sorry.
Is there an expectation somewhere?
There should be an expectation somewhere. Right, I think, yeah, this looks correct. And let me just check it. Check this expression with the book.
So the conditioning is inside the expectation at the end, right?
So this is,
But there's this conditioning on IO at the end, but that's part of the expectation.
that is part of the expectation, yeah. I guess my expectation should be outside.
yeah.
So let me take the expectation outside.
Although it doesn't apply to G mu.
Right, this one is a scalar quantity, so it doesn't apply to that.
so the 1 over t doesn't.
T. Right. Okay, so in some sense, this particular quantity is looking at whatever the transient cost you have accrued minus the steady state cost that you would have accrued if you had accrued this cost throughout the entire horizon. Take the difference, that gives you your V mu. Okay, so another way to think of V mu is V mu equals to summation t equals 0 to capital TC minus TG mu plus some error that goes to 0 as t goes to infinity. This one should also have an expectation here. Okay, and this error goes to 0 as capital T goes to infinity. Okay, the proofs of all of these results are going to be fairly involved, so I won't cover these proofs in the class. I did cover it in the previous, when I taught it in spring 2020, so those videos are on YouTube. But in this class, I don't want to cover it. I want to spend more time on understanding all of these mechanics. Any other question? Yes.
So this du, b mu, it's like you've taken the expectation over I0?
No, I'm not taking. So this is the function notation. So this is a function on this side. This is a function given I0. And this is the constant, and this is the error term.
Because v mu is sort of like a vector, and then you're accessing one element above, but now below, I guess.
Yeah, so that's why I need to add I0 on both sides, or I can write it in a function notation where I suppress the dependence on I. So then it's just a function. Does that make sense? No?
Then it's random, because I0 is random.
Right, so that's why there is this error, which is a random quantity, but it goes to 0 almost surely as t goes to infinity. Right.
I'm just trying to understand the notation.
Yeah. Yeah, sometimes I want to write it in a functional form, sometimes I want to write it in a scalar form, so it just, I have to switch notations. And it really depends on which book you are reading. Some books are writing it in a function form, some books are writing it in a scalar form. So yeah, it's just collecting information from multiple books becomes a challenge. But this is another way to think about it, which is the transient cost minus the steady state cost gives you the value function. And if you're looking at only a finite t minus 1, if you're looking at a finite time performance, then there will be some error, but those errors will go to 0 as capital T goes to infinity. Okay? Now I want you to notice one specific property of this operator T mu, which again was not the case in the discounted case, but this sort of appears in the average cost setting. What happens if I add a constant to V mu? What happens if I add a constant to V mu? Okay, so let's think about it. I add the same constant to the entire vector. So remember, V mu is a function, or you can think of it as a vector, and so I'm adding the same constant to every element of that vector. This one doesn't depend on V. I'm summing it all up, but the probability sums to 1. Okay, so if I add a scalar quantity here, I'll get the same scalar quantity here. So in some sense, V mu is not unique. So G mu is unique, but V mu is not unique. So what I mean is, so this is a unit function. So 1 of S I equals to 1 for all I. Some books use E to denote that function, but I'm assuming that we will need E at some point of time in the future to denote error. So that's why I'm using this notation. So this is a unit function which takes a value 1 for all I. So I add a constant k to the value function, and it turns out that v mu satisfies this sort of condition where you add a constant and it's still a fixed point of this particular operator t mu. Okay, so v mu is not unique. G mu is unique. V mu is not unique. This is known as a gain. This is known as a value. So gain is unique, value is not unique in the average cost case. Okay. Okay, so this is the result for the unichain case. I want to show you what happens in the case of multi-chain MDPs. So if there are no questions on this, I want to erase the board and then I want to look at some results. Okay, yes?
I guess I have a question, unichain versus multi-chain. So if there's some sort of class of recurrent states, isn't it like I can choose to partition it into two or not? So I'm wondering like how exactly how you distinguish that difference.
So you know in the recurrent class, all the states will be visited infinitely often.
All the states.
All the states. So
Okay.
that's what a recurrent class would mean, that all the
Got it.
states have to be visited infinitely often. In the transient, it will be visited finite number of times, and then
Okay.
we'll be out of that. Yeah. So there is the stopping time. You set the stopping time, then the probability of stopping time is less than infinity is equal to 1 for transient states. I don't assume everyone has taken probability theory class, so that's why I'm not using all the stopping time definitions that are prevalent in this literature. Can I erase this side of the board? Okay, so let's look at what happens in the unichain case, and I'll give you the intuition as to why there is a unique G mu in this particular situation, and what happens in the multi-chain case. And while I'm not going to prove the results, the proofs are fairly laborious and you can find them in the books. I want to start with an example. So I have a transition kernel. So let's assume that there is a single strategy. So we are not doing any optimization here. Zero 0.2, 0.8, 0.1, and 0.8, 0.2. So how do I read this matrix? P. This is Pij. So my starting state is I, my next state is j, and this gives me the transition probability. So P j equals to 1 given I equals to 1 equals to 0.2. P j equals to 1, I equals to 3 equals to 0. So if I start with state 3, so this is my state 3, this is my state 1, 2, and 3. So if I start with state 3, what's the probability that I'll end up in j equals to 1? And this is I equals to 1, I equals to 2, I equals to 3. So this is how you read a transition matrix. So this is a transition matrix for a 3-state Markov chain. And let's look at what p raised to infinity looks like. So this is the transition, this gives you the transition probability. If you start with state 1, what's the probability that the next state is going to be 1? So if what generally happens is you want to find out what's the probability that it equals to I or j given I0 is equal to I. You know how this probability gets computed? This is basically p raised to t plus 1. So because I'm taking it here, no, I1 would be, okay. So p raised to t, and you look at the ijth component of this matrix. Okay. So you have the transition matrix, you take transition matrix raised to t, you get another transition kernel that looks somewhat different. Of course, it's going to look different from this, and it gives you what's the probability. So ijth element of this matrix is going to tell you what's the probability that you started from ith state, what's the probability that after t time step you will end up at jth state. Okay, so this is what the transition matrix looks like, and if you look at this transition matrix, your p raised to infinity is going to look like so it has a pretty good structure. This is this can also be decomposed at this as this matrix. So you can look at what the transition structure looks like after infinite number of time steps. So which is a transient state and which is a recurrent state in this particular MDP? Or it's not a DP, like there's no decision here, it's a Markov chain. But I want you to comment on which states will be visited infinitely often and which states will not be visited after a certain number of time steps. Okay, so what is this? This is p I infinity equals to j given I equals to whatever, I0 equals to I. That's what this matrix is, right? So I'm starting from this state. What's the probability that I'll be in state 1? 0. I'm starting from this state. What's the probability that I'll be in state 1? 0. And I'm starting from the third state. What's the probability that I'll be in state 1? 0. Okay, so eventually I'm not going to be visiting the first state at all. Okay, no matter which state I start from, I'm not going to be able to visit the first state at all. Okay, so in this case, your transient state is 1 and your recurrent state two and 3. Okay, so I have a single transient state and I have 2 recurrent states in this case. So if I am in state 2, next time step I'll be in state 3. If I'm in state 3, next time step I'll be in state 2 with probability 0.8 and I'll be in state 3 with probability 0.2. Okay. So once you get into this class, you don't go out of this class. So this part is 0. So transitioning from state 2 and 3 to state 1 is 0. So you can see it just by looking at the transition matrix. You can figure out which one is going to be a recurrent class and which one is going to be a transient class. Okay, and you can also see it in P infinity. Okay, so the transient class will have probability 0 after infinite number of time steps, whereas the recurrent class will have a positive probability after infinite time steps. Okay, so this is a unichain Markov chain because you have a single recurrent class and you have possibly empty set of transient states. So in this case, we have one transient state, but you could have an empty set of transient states as well. But you have a single recurrent class, so it's a unichain MDP. Because the transition structure, the transition matrix after infinite number of steps has this sort of structure where you have 1, 1, 1 getting multiplied with the invariant distribution. That's the reason why you have a unique G mu, because this G mu actually depends on this particular matrix, 0, 4 by 9, 5 by 9. So this G mu is directly related to this matrix, which basically tells you how much time the Markov chain is going to spend in state 2 versus state 3. So that leads to G mu. V mu is not unique, and that's just by virtue of the Bellman operator property. So this is something we can see easily, but this one is, the reason why it's unique is because of this reason. Let's look at a multi-class MDP, okay? Not MDP, but Markov chain, yeah.
Although you said G mu is unique, but it depends on the policy mu, right?
That's right.
Okay.
That's why it's a subscript mu.
Okay.
Yeah. We'll talk about G mu star, so what happens at the optimal policy.
Does P infinity always have this factorization in the rank 1?
Only in the unichain case.
Okay.
Yeah.
And so like the rank of that is the number of recurrent classes?
Not quite the rank of this. I mean, this is always one rank, right? So because it's a single row, but the number of non-zero elements are the recurrent classes.
I mean, is in a multi-chain case, if you have 2 multi-chains, then that would be rank 2. If you have 3
Yes, so we'll see the next, yeah, exactly. So you will see some such element in that case. So let's look at a multi-chain MDP. Or not, again, I'm saying MDP, but I'm really looking at MDP with a specific policy. So my transition matrix looks like 0.2, 0.5, 0.3, 0, 1, 0, 0, 0, 1. This is a multi-chain MDP, so let's do P raised to infinity. 0, 0.62, 0.38, 0, 1, 0, 0, 0, 1. Okay. Okay, so this is the transition structure. I start from state 1. I remain in state 1 with probability 0.2. I transition to state 2 with probability 0.5. And then I transition to state 3 with probability 0.3. But if I'm in state 2, I'll always be in state 2. If I'm in state 3, I will always be in state 3. Okay? So think of, just to be able to think easily, let's assume that we are in an economy where if you are in middle class, you remain middle class with probability 0.2, but then you can become rich with probability 0.5, and you can become poor with probability 0.3. And once you become rich, you always remain rich. Once you become poor, you always remain poor. Okay? So think of it that way, that way it's easier to visualize. So what happens in this particular economy after infinite number of transitions, okay, after infinite number of days? If everybody started from the middle class, with probability 0.62 they became rich, with probability 0.38 they became poor. Whoever started as rich remains as rich, whoever started as poor remains poor. Okay, so that's what this multi-class means. So now there are two recurrent classes. Just the state 2 and just the state 3. So if you are in 2, you always remain in 2. If you are in 3, you always remain in 3. And what's the transient class? That is 1. There is no middle class in this economy after infinite number of transition. Okay? People either end up becoming poor or they end up becoming rich. Okay. So what does these rows mean in this case? So if I started with state 1, this is the invariant distribution. If I started in state 2, then this is the invariant distribution. So if my initial state, right, at time t equals to 0, if I started from this state, this is what my distribution, invariant distribution is going to look like. If I started from state 3, this is what my invariant distribution is going to look like. As a result of which, the theory for multi-chain MDP is very, very involved, very long proofs, very complicated structure that you have to parse through. As a result of which, you will not have a unique, so the gain, so G mu will be different depending on which state you started from. So if you started from this state, you will have one specific G mu. If you started from this state, then you will have a different G mu and so on. So G mu will become a function of state. It will no longer be a scalar quantity. And V mu, of course, is a function of state, and it's not scalar to begin with. But in the multi-class case, this is no longer a scalar quantity. It becomes a vector quantity. It becomes a function of the state that you started with. Okay? But this will be the average cost from state 1, state 2, state 3, and so on. And this is always the difference which is given by this particular term. But we will not talk about multi-chain MDP in this class, except for when I talk about Blackwell optimal policies. So I'll tell you how do you deal with problems of this type. One way to deal with problems of multi-chain, but we'll talk about it in a bit. Any questions so far? Yes?
So you say when for multi-chain, G mu is a vector.
Right.
Is a vector still unique? Is a vector still unique?
For a mu, it is definitely unique. For a specific, yeah. So for every mu, there is a unique vector G mu, which gives you the average cost for every possible initial state that you start with. Okay. Any other question? Okay. Okay, so let's look at a value iteration algorithm for this. So there is a problem here, and the problem is, so in value iteration algorithm, of course, we are doing the minimization, but one of the problem that I have here is that the Bellman operator has this property where if you add a scalar to a value function, it's still a fixed point of the operator. So while I'm erasing the board, I want you to think about how would you come up with a value iteration algorithm for a Bellman operator of this type, where if you translate it with a scalar quantity, if you add a constant function to the original value function, it still remains the fixed point of the operator. Yes?
So does that theorem still hold true even in the multi-chain case?
I'm pretty sure it holds true, but I haven't checked it today. Okay? But I think this because this statement is fundamental and this comes from the statement of the Bellman operator, I think it will hold true even for the multi-chain case. But I'll have to check the reference to make sure that what I'm saying is correct. Okay, so the question for you is, how would you do value iteration in this case? In the case of shortest path and in the case of discounted cost, we knew that there is a unique fixed point of the operator t, but that is not the case here. So what should we do? So let's look at the wrong value iteration algorithm for this. I start with V naught and then my Vk plus 1 equals to tvk, and the operator T is min u in ui summation pij mu piju ciu j plus bj. Okay, so this is my Bellman operator. The only change I have done here is no longer, there is no alpha here. Okay, there is no discount factor here because it's the average cost setting. What is the problem if I run this algorithm? If I pick Vk plus 1 equals to tvk, what problem would I encounter? So I pick an initial value function and I keep running this iteration over and over again. The only difference in this particular operator is this operator doesn't have a discount factor. So I don't have a unique fixed point of this, and even in this case you will notice that T v plus k 1s equals to v plus k 1s. So even this particular operator satisfies this condition. So I know with certainty that there is no unique fixed point of this particular operator T. So why is this the wrong? So there are two questions. Why is this the wrong iteration? And the second question is, how do you fix this iteration?
May stuck.
Sorry?
May stuck. For some values.
It will, what, so you're saying it will not converge, it will diverge?
No, it will stuck for some settings, I guess.
It'll get stuck?
Yes, stuck for some settings.
Not quite. So I'm still, by the way, I'm still in the unichain case here. Any other thoughts? Why is this the wrong value iteration algorithm? Okay. So I have a cost. So sorry, I start with some initial value function. I added a cost, took the minimum. So there is some positive number that gets added to the value function. Then in the second iteration, again some positive value gets added to the function. In the third iteration, some positive value gets added to the value function. So what happens if you keep adding a positive number to an existing number and you run it for infinite number of steps? It scales to infinity. So this iteration is actually going to infinity no matter what V0 you start with. So it's a diverging iteration. We get a diverging sequence of function. So how do we fix it? Remember that our goal is not to get just the value function. Our goal is to get the argmin, right? Argmin is what we care about. Argmin is what gets implemented in real world. So minimum is just a way to get to the argmin. So I want to get to the argmin. I don't care about the minimum value as such. I care about getting to the argmin as soon as possible.
Average?
No, not average. Average is what we want to compute, right? G is what, G and V, these are the two quantities I want to compute. G star and V star. Yes?
You just project away from the null space.
Right, so there is a projection, but what sort of projection would make sense? That's
Take the average and subtract it.
right. So actually, technically, you can just subtract any constant function from the value function, and that will still work. So what we are trying to do is, I get some positive number. I'm going to subtract something from this particular function, and I'll keep going the iteration. I'll keep doing the iteration in the same manner. So that's called a relative value iteration, which is the correct So here you have Vk plus 1 equals to tvk minus Vk of I0. So you pick some reference state, I0, and you subtract a constant function. This is a constant number. I'll multiply it by a constant vector, so I get a constant function. And every time I apply the Bellman operator, I subtract a constant value from this particular function, the output of the tvk. And this one actually converges to V star. And then you apply TV star, you get G star plus V star. This is the correct value iteration algorithm for average cost case. Okay, it's called a relative value iteration. This word relative means that with reference to this reference state I naught, I'm finding the relative value function with respect to this reference state, and that's why it's called a relative value iteration. So in the steady state, my V star of I0 is going to be 0 because I have been subtracting the value function from that particular I naught.
So does I0 need to be the starting state, or it's
Any state.
Okay.
Just pick, oh sorry, this I naught, maybe I should write it as I ref. It could be any reference state that you pick. And you can definitely pick the starting state as the reference state, not a problem.
So even if it is a transient state, it is still okay.
It doesn't matter because G mu is unique,
Yes.
right? So even for the transient state, you get the same average cost. So remember, what happens in the transient state is you keep accumulating the cost of the transient state, then you get into the recurrent set, and then you only accrue cost of the recurrent set, okay? And then you average it out. So whatever cost you accrued for the transient state, when you average it out over an infinite horizon, that cost is always equal to 0. So it doesn't matter what cost you have accrued in the transient state. You only care about the cost that you have accrued in the recurrent state, okay? So that's why G mu is the same. G mu is the average cost, even if you, no matter whether you start from a transient state or a recurrent state, it still is the average cost that you are going to incur. And that's why it's unique for all the states. And this is all the case for unichain MDPs. For multi-chain, things becomes, again, very complicated. Okay.
This only works for unichain.
This only works, relative value iteration only works for unichain. Okay. Any other question? Again, there are generalizations of these results. So if you look at the literature, you will see a lot of different assumptions, different modifications of these functions, and some solution and some proof, but we don't want to cover all of that in the class. Okay. Any other question? Okay. So this is relative value iteration. It converges to a fixed point V star eventually, like as k goes to infinity. What does that tell you? It tells me, given that there is this operator and this operator converges to a fixed point, it tells me that there seems to be a norm under which this map is a contraction. Okay? So what is that norm? And what's the condition for the contraction? So when does relative value iteration converge to V star? And what's the norm under which it's a contraction? So remember, when I was talking about Banach contraction mapping theorem, one of the things that I mentioned was many a times it takes a lot of effort to figure out what norm is it a contraction over, right? So you can come up with a function, but finding the norm over which that function is a contraction is an art in itself, and so that's the art I'm going to be talking about today. Okay, so I'm going to define this norm on the space of value function. So this is the space of value function V from S to R, which is the same as R to S, and I'm going to endow it with a span semi-norm which is defined as span of V as max over I of Vi minus min over J of Vj. So I have a value function 532. What's the span of V? So span is a seminorm. I have defined this seminorm over the space of value functions V. The span is defined as the maximum element of the value function minus the minimum element of the value function. Okay. So what is span of V? What's the maximum element and what's the minimum element? It's not a brain teaser. Come on, guys. Somebody should be able to answer. What is the span of V? 3. So 5 is the maximum value of the value function, 2 is the minimum value. So I do 5 minus 2 equals to 3. If I pick V equals to 5, 3 and minus 2, the span of V is 5 minus 2 equals to 7. Okay, so that's the seminorm. Why is it a seminorm? What's a seminorm? So one of the reasons, one of the things that seminorm satisfies or doesn't satisfy in comparison to a norm. So remember, if norm of a vector is 0, then the vector has to be 0, right? That's the property of a norm. It's a seminorm because you can have a non-zero vector whose span is 0. So let's look at an example of a vector V equals to k, k, k. What's the span of V? So this is equals to k of yes 0, right? So maximum element is k, minimum element is k, k minus k equals to 0, so span is 0. So it's not a norm, it's not a norm, it's a semi-norm. Okay, so turns out that this operator that we talked about is actually a contraction with respect to the span semi-norm. So I'll write it formally. Okay, let me write it here. Okay, R V I Now I'll write another condition. So I have alpha, which is a function of p, which is 1 minus min iu I prime u prime of summation j in S, minimum of p j given iu then span of t v1 minus t v2 is less than equal to alpha p times span of v1 minus v2. This is for unichain. So somebody in 1960s must have spent half of their PhD trying to identify the conditions for unichain MDP under which the value iteration algorithm is a contraction with respect to a semi-norm, and the contraction coefficient is given by alpha p. Okay, so this is a stronger condition than unichain because it requires certain thing to be strictly less than 1, right? So I want my alpha p to be strictly less than 1. That's one of the assumptions. So the MDP has to be unichain, the cost has to be bounded, the alpha p has to be less than 1, in which case relative value iteration will converge to V star. This will converge to V star. So unichain alpha p less than 1 implies that relative value iteration will converge to V star, which is the optimal value function for the average cost MDP. So under a lot of restrictive conditions, we have been able to identify a set of sufficient conditions under which the value iteration algorithm, or rather relative value iteration algorithm, would work in the case of average cost MDP. And that's the reason why average cost MDP is not studied as much, because it requires a lot of assumptions and care. Any question?
So that's for the alpha p minimum. IU and
Any two state action pairs, pick any two state action pairs, look at the minimum of the transition probabilities. So this is minimum of the two transition probabilities, and then you sum it over all future state.
I mean, we can understand as to pick any two policies.
Pick any two policies. Yeah, you can think of it that way as well. Yeah.
Professor?
Yes.
Well, the contraction theorem is the classic sequence. So this sequence is not the classic sequence.
It's not a norm. Yeah, that's right.
So it's not, because it's not norm, so it can't be a classic sequence. So I question the existence of the fixed point.
Yeah, so that's a very good question. So the question is, which again part of my postdoc work was to try and figure that out. So the question here is, you have a semi-norm, you have a contraction operator with respect to a semi-norm.
Yeah.
How does that converge to a fixed point? Because in Banach contraction mapping theorem, we required the function to be a contraction with respect to a norm, okay, not with respect to a semi-norm. Anyone wants to answer that question? So I spent several months working on this mystery. It was mystery to me when I first saw it. It wasn't a mystery later on. So anybody who has taken a functional analysis course? No? Real analysis? Anyone who has taken real analysis? Just okay, not many students have taken it. Okay, so you define what is known as a quotient space. So I don't want to go into the math of this. So Vs, where you pick two elements, you define an equivalence class of V, which is V plus K1S. So you define an equivalence class, and this is called a quotient. This is called a quotient space. This is known as an equivalence class of function. So pick any point V within this equivalence class, and you get a unique. It's considered a point in the space, in the quotient space, and so T becomes a contraction in this quotient space, and this quotient space is a complete space, complete metric space. So therefore all of that theory still applies. The Banach contraction mapping theorem still applies, but it doesn't apply in the original value function space, it applies on the quotient space. But again, for the reason why I'm telling you these words is so that you can go back to Wikipedia and you can study like a long article on what quotient space actually means, but I don't want to go into the theory of quotient spaces in this class. Okay, it's a complicated theory. So semi-norm becomes a norm under the quotient space, and this operator T, Bellman operator, becomes a contraction in this normed space, in this quotient space, quotient normed space. Okay, and that's why this converges to V star. Okay. Any other question? Okay, so no further questions. So let's talk about what happens. What if you are exposed to a problem with a multi-chain sort of structure? Then how do you solve? Because I know some students are from economics department here, and so if you are from economics department, you're quite likely to encounter a problem where there is a multi-chain structure. So then what do we do? So the simplest thing to do in those cases, if you have a multi-chain structure, is to just consider the discounted case. Okay, so then you don't have to worry about the multi-chain structure. But let's say your supervisor, manager, advisor, whoever is above you wants you to look at the steady state performance. They don't want you to look at the transient performance, right? So remember, you pick discounted problems when you are interested in transient performance, and you pick average cost problem when you are interested in the steady state performance. So your supervisor said, I want you to look at the steady state performance. I don't care about the transient performance of this particular MDP. So then what do you do? So Blackwell I'm not quite sure, but if he came up with the results, it must be in 1960s or 70s, because that's when he was very active. He came up with this notion of Blackwell optimal policy. So before we talk about Blackwell optimal policy, let's see what happens when I have a discounted cost problem. So I have a multi-chain MDP, and let's say I have a discount factor. I create this table of discount factor and the set of optimal stationary policies. So I pick alpha equals to 0.9, and I see that the optimal stationary policy is mu1 star and mu2 star. Then I pick alpha equals to 0.98, and my policy is actually changed to mu3 star and mu4 star. And then I pick alpha equals to 0.999, and my policy is, optimal policies are mu3 star and mu5 star. And then I pick alpha equals to 0.9999999, and my optimal policies are mu3 star and mu6 star. Okay, I don't want you to note it down, just look at the board. These are all arbitrary numbers anyways. What do you notice? What's the interesting thing that Blackwell noticed back in 1960s?
As alpha converges to what? The policy converges?
No, the policy is not converging, right? The set of optimal policies are changing. But what still remains the same?
Use 3 dissolves.
Yeah, mu3 star. So there is a threshold. There is a threshold after which there is a policy that seems to be optimal for every discount factor. Okay? So mu3 star is called the Blackwell optimal policy, and it turns out that mu3 star is an optimal policy, optimal for average cost. So mu3 star is an optimal policy for average cost MDP. Okay? Remember, for discounted case, I didn't have to make any assumptions on the transition structure, multi-chain, single chain, recurrent class, non-recurrent class, and all of that stuff. But what Blackwell noticed is that there is a alpha bar above which you have a policy that always exists. So Blackwell optimal policy always exists, and it is also optimal for the average cost MDP. Okay, so that was the main result he proved. He recognized the existence of a Blackwell optimal policy, and he established that it is optimal for the average cost MDP as well. Okay, under no assumptions, like as long as everything is bounded and the value iteration converges, which converges under fairly general conditions for the discounted case, you will have a Blackwell optimal policy.
So when we have like two different optimal policies, is it because of the initial state? If the initial state is in one set?
No, the reason why I wrote 2 is because you could have multiple optimal stationary policies. So let me go back to this equation. So if you have alpha here, the argument could be multiple actions. You could have multiple actions that achieves the argument at V star. So let's say this is V star.
Is this for multi-chains or?
It doesn't matter. I mean, I'm looking at the discounted cost setting. So the chain structure doesn't really matter in discounted cost. So that's why let's write it as V alpha star, because this is the optimal value function under the discount factor alpha. So you could have multiple optimal policies here, which depends on what is the argument here. If you have 2 or 3 actions that are in argument for 2 or 3 states, then you could have multiple policies that are optimal, okay? Because it still satisfies the value iteration, the fixed point equation. I don't know if that, I have some time, so let me go over it very quickly. So the question is, why do we have multiple optimal policies there? Is it because of the multi-chain case or uni-chain case? But it has nothing to do with multi-chain and uni-chain. So let me think about it in the following way. So I have V alpha star is the optimal value function with discount factor alpha.
So is that unique, or there can be several of those?
So V alpha star has to be unique.
But like over here, you have a single alpha star and you have multiple.
No, I have multiple alphas. So alpha is the free.
Alpha 0.9, you said you have 2 optimal policies.
Yes, so that is the case with alpha equals to 0.9. That's a different value function. For different alpha, you have a different value function. You won't have a single value function for all alpha. Okay, but let's look at the argument. Okay, so mu, remember mu I equals to the argument of u in ui of this big summation. Now let's say my argument, let's say I have 2 states. So S is equal to 1 and 2 and u equals to 1 to 10. So my argument of u in u1, the set is 3 and 4. So there are 2 actions that are optimal at state 1, and then argument of u in u2 equals to 6 and 7. Okay, so I have two actions that are argument in this value iteration. In the Bellman operator. So I have 2 argument here and I have 2 argument here. I can construct policies in the following fashion. So I have mu1 star where I pick equals to 3 equals to 6, and then I pick mu2 star 4 equals to 6. So I picked two policies. In one policy, I deterministically mapped state 1 to action 3 and state 2 to action 6. Then I picked another policy where I mapped state 1 to action 4 and state 2 to action 6. Both of these are optimal policies because they are all part of this argmin. So mu1 star, so 6 is an argmin of this Bellman operator thing. So you can have multiple policies. So for every alpha, depending on how you have constructed the policy, you can have multiple policies that are optimal. But Blackwell optimal policy is beyond a certain alpha bar. That policy will always be optimal no matter what alpha you pick.
So optimal policies, so there can be just one optimal policy. It can be multiple. So
Yeah, at least one is guaranteed.
at least one is optimal.
Yeah, at least one is optimal, but you can have multiple policies that are optimal as well.
If it always has just one unique optimal, then it is Blackwell, right? If it is.
For all alpha. Okay, so alpha has to change. So what is the definition of Blackwell optimal policy?
It's one of the optimal policies, right?
So there exists an alpha bar in 0, 1 such that mu star is optimal for all alpha in alpha bar 1. Okay, so there is a alpha bar, a threshold, which is this alpha bar, so somewhere around 0.95, so that after you pick any discount factor between 0.95 and 1, mu star will still remain optimal, okay, for all of those different values of alpha. Okay, that's the definition of Blackwell optimal policy, and what Blackwell established is there always exists a Blackwell optimal policy, and that is the optimal policy for the average cost case. Any question? Yes, please.
So after the, I guess regardless of the threshold, is it always necessary that the number of policies stay the same, or can it like vary?
No, you can have any number of policies here, but there is at least one policy that will remain the same for all values of alpha. Okay, at least one. You can have multiple policies that are common across these values of alpha, but you want to pick the one that is Blackwell optimal. And the reason why, so in some sense, Blackwell optimal policy optimizes the transient behavior and optimizes the steady state behavior. So in some sense, Blackwell optimal policies are better than just any optimal policy because it satisfies the condition that it's also optimal for the discount factors close to 1. So the theory of reinforcement learning to compute Blackwell optimal policy is not well developed. Not many people study this topic. So it's certainly an open area for research if you're looking for a research problem. Because of this attractive property that it optimizes the transient behavior and the steady state behavior, so it's pretty cool, and it works for multi-chain case as well. Okay, so there is a reason why people should study reinforcement learning for computing Blackwell optimal policy. However, I would admit that the literature around this is very scant, so it's not something that people study very often. Okay. Okay. If there are no questions, I think we can end the class now, and I'll see you on Thursday. Thank you.